Welcome to our channel in a video from our collection High School Calculus Selected Exercises. We want to prove the implication shown on the screen. First of all, it is easy to verify that the function fx equals 1 over x squared plus 1 is a solution to the given equation for the given initial condition. We will stress on the trickier part, that is, to prove uniqueness. Let f be a differentiable function satisfying the given equation and initial condition. Let I be an interval containing 0. We will first show that if the function f has no roots in the interval I, then fx equals 1 over x squared plus 1 for every x in the interval I. Indeed, in the interval I, we can write minus f prime x over fx squared equals 2 times x, which, by virtue of standard differentiation rules, becomes 1 over fx primed equals x squared prime. In the interval I, we get 1 over fx equals x squared plus c. So, since f0 equals 1, we obtain c equals 1, and our first target is attained. If f has no roots in the real numbers, then the proof is complete. On the contrary, suppose there exists a positive xi such that f xi equals 0. The treatment of the case of a negative xi is analogous. We observe that f primed is non-positive for every non-negative x, hence f is decreasing in the closed interval from 0 to plus infinity, though not necessarily strictly. Consider the continuous function h on the closed interval from 0 to xi, which is described by the formula hx equals 1 over x squared plus 1 minus fx times fx. H is 0 for x equals 0 and x equals xi. There are three cases. First case, h is everywhere 0 on the closed interval from 0 to xi. Second case, h takes a positive maximum value on the closed interval from 0 to xi at some eta in the open interval from 0 to xi. Third case, h takes a negative minimum value on the closed interval from 0 to xi at some eta in the open interval from 0 to xi. We examine each of these cases. First case, for every x in the closed interval from 0 to xi, either fx equals 1 over x squared plus 1 greater than or equal to 1 over xi squared plus 1, or fx equals 0. Hence, we get the following conclusion for the set of values of f on the closed interval from 0 to xi. Since f xi equals 0 and f0 equals 1, the intermediate value theorem is violated, as f is continuous on the closed interval from 0 to xi and does not take values on the open interval from 0 to 1 over xi squared plus 1. Thus, we get a contradiction. For the second and the third case, it follows that f eta is not equal to 0. The monotonicity of f implies on the one hand that f eta is positive, and on the other hand that f has no roots in the closed interval from 0 to eta. Therefore, according to what we showed at the beginning, on the closed interval from 0 to eta, it must be that f eta equals 1 over eta squared plus 1, whereby we get h eta equals 0, which is again a contradiction. This implies that xi does not exist. At this point, the exercise is complete. Thank you for watching.